Again, the requirements that mathematical model puts on the physical implementation of a quantum computer are the continuum of states. We already discussed this, and it is quite easy to implement. The true randomness. We can do it as well. And the interference. Well, what's this? We have just seen that if some event is truly random, then mathematically it means that we can control and distribute the computations using this event. So, if we have some function f which takes one bit as an input, second, the device which implements this function f, and third, this device can take qubits as its input, then we can feed the qubit in the state plus to this device. And since the state plus is really a superposition of two states, 0 and 1, then our device becomes an observer of this state, which means that there are going to be two types of this device. One of them observes 0 and acts on 0 qubit, while the second one observes 1 and acts on the qubits in the state 1. And for each of these devices, the value of the qubit which is fed to them seems random. And look, we just had a simultaneous computation of function f on both available inputs in just one run. Looks good, doesn't it? Well, yes, it looks good. But many of you probably ask yourselves, why we never observe such a thing like one computing device becomes two or more computing devices? Or one cat becomes two cats immediately, without any signs of a reproduction process? Well, it's quite obvious, and if you listen carefully, you probably already know the answer. You can try to observe these two cats or two whatever else, but as soon as you do, you observe only one of them as a random event, since your identical copies become different. They split on this event. The other question could be, well, I can't observe the second cat because another me observes it, but why can't I observe another me observing that another cat? Well, it is a tough question indeed. As soon as we admit that these different probabilities of an event are actually implemented somewhere, the next natural question is, where? And I'm not able to give you the answer to this question. I'm not even sure that the statement of the question in this form is correct, since the word where is strongly connected to our usual perceivement of the space as some three-dimensional something around us. The German philosopher Immanuel Kant even stated that this concept of the space is immanent to our brain, not to the real world itself. And the real world itself is maybe something very different. Anyway, the American physicist Hugh Everett III in 1957 proposed this new concept of a multiverse. Some large enough, probably infinite stack of universes, which are in some sense parallel. The term parallel here refers to inability of objects in the different universes to interact with each other. At first, somewhere in the beginning of the time, if such thing even exists, the beginning of the time, all these universes are identical. But in time, random events occur which divide these universes into different types, depending on the results of these random events. So, when we observe some random event, our previously identical copies in different universes start to differ, and these different copies from now on can act and compute differently. And we cannot interact with each other, since we are in different universes. So, though there is so much of available computing power in this multiverse, we are not supposed to be able to use it, since there is no way we could collect the result of this distributed computation. Right? Well, fortunately, sometimes we can do that. And this can be done through the process physicists call interference. To understand what interference is, we have to return to Young's experiment. But now we are going to remove these two detectors and place another screen here. This new screen is able to detect electrons in every its point. When an electron arrives somewhere at this screen, it will give us a flash, so we would be able to see where exactly the electron has arrived. It is the same kind of flash which surprised the cat so much in our previous reasoning. So, we are going to observe the flashes, and we are going to count them to see where electrons arrive more often. And again, for our convenience, we are going to shoot the electrons one by one. So we are going to comfortably count the flashes. At first, we will try to perform this experiment with only one slit open. On the slide, you can see what we get when the higher slit is open and when the lower slit is open. The height of the graphs on the right is proportional to the number of electrons arriving at the corresponding areas of the screen. The result is, as one could have expected, closer to the straight lines, we get more electrons. But when we open two slits, the result changes dramatically. Of course, if the parameters of this set are tuned properly. The result is contrary to the obvious. We open another slit, and we allow more electrons to arrive to this screen. And indeed, more electrons arrive, but there are, for example, areas where before we saw flashes, and now we don't, as if something prohibits the electrons to arrive to these sectors. With just one slit open, there were no problem for an electron to go there. But when we open the second slit, something happens, and suddenly it just can't go there anymore. Can we explain why?